Today we have to discuss work and energy in electrostatic system. See, what is work and what is energy? How you have defined energy? See, when you have read energy for the first time, what is the definition that you have used for energy? See, we have read this energy in 7th or 8th class as far as I remember, and there we read about energy is, I write a very simple definition. Energy is the amount, ability to do work is called energy. Energy is ability to do work. So energy is ability to do work. Means if you want to do work, you must possess energy. Like if suppose we want to push this mass, 10 kg mass, and I am applying say 10 Newton force, and I push this, and when I push this, it covers a distance of say, it has reached a distance of, it covers a distance of say 1 meter. Then we say we have done 10 joule of work. If I apply a constant force and the object has moved by a distance of 1 meter, I simply say the work done by me is force into distance, that comes to be 10 joule. See, when I do this 10 joule of work, 10 joule of energy will get deducted from our body, and it will convert into either kinetic energy of this object, or its kinetic energy may further get converted into work against friction. So when you do this 10 joule of work, you must possess energy which should be more than or at least equal to 10 joule, because when you do work, a part of your energy or 10 joule of energy, whatever work you do, that amount of energy get deducted from your body and it will appear into some other form. See, energy do not get destroyed. When you do this 10 joule of work, your energy, your 10 joule of energy will get converted into kinetic energy. If there is no friction, all 10 joule of energy will get converted into K. The K of the object will be 10 joule. If there is a friction, some part of the work done may go into work done against friction, and that may convert into heat. So partly it will appear as kinetic energy, partly it will appear as heat. So everywhere you will find, whenever you do work, work is a mechanism where the energy from one form will get transformed into other. Energy from one form gets transformed into other. So that's why we define work is ability to do work, or energy is ability to do work, is called energy. So that's a good definition that still holds good. In this chapter we will be studying about energy, work and energy. We will be studying, we will be seeing several questions where we will find that electrostatic energy will get converted to some other form, or some other form of energy will get converted into electrostatic energy. So here we are into a system of static charges. So static charges, here you don't have a charge in motion, so there is no question of kinetic energy. Here we will be talking about, see here the energy which a system will possess will be only due to by dint of its configuration, because the charges are not moving, charges are at rest, right? So the energy which system will possess will be by dint of the configuration. This electrostatic energy is nothing but electrostatic potential energy. This is the form of potential energy, right? Now first of all, let us define electrostatic energy. Let's define what is electrostatic energy. I'll call it electrostatic potential energy. I'll call electrostatic potential energy. Before I go into electrostatic potential energy, first let me discuss about potential energy, how to find a potential energy for a system of particle. How you find the potential energy for a system of particles. How to find this potential energy for a system of particles. Say for a system of particles, how do you find the potential energy for the system of particle? See, potential energy characterizes one of the basic attributes of the system, that is configuration. It characterizes configuration of a system. Characterizes configuration, right? What is configuration? Configuration of system is how the particles are arranged. Configuration basically tells you how the particles in a system are arranged, how the particles are arranged in a system. That is characterized by potential energy, right? How the particles are arranged. Now before finding potential energy, suppose we have to find out the potential energy of the solar system. So I take a system, a classical system. Suppose we want to find the potential energy of the solar system. It consists of Sun and 9 planets. People told me that there are 8 planets, but I still consider 9 planets. Still I see Pluto, so I consider it 9 planets, right? Definition has been changed. One day you can even keep out Earth by changing definitions. I don't believe in this, so I still assume there are 9 planets. It's Sun plus 9 planets. Suppose these are the 10 particles for which I want to find out the potential energy. Suppose we have to find a potential energy for a given configuration. For a given configuration, I want to find the potential energy. Before you find the potential energy for a given configuration, see, you can find the potential energy only when, see, it's true for any quantity in fact. If you want to find out the potential energy, first of all you define a configuration for which you will assign 0 potential energy. First of all, you try to find out a configuration. See, you are given a configuration for which you have to find potential energy. Before that, first of all, you try to define a configuration for which potential energy is 0. Right? What can be that configuration? See, potential energy is 0 means what? Potential energy, I can assign potential energy 0 to what kind of configuration? For the same system, Sun and 9 planets, what could be the configuration of Sun and 9 planets for which I can assign 0 potential energy? A configuration where they are not interacting. See, whenever you have a system of particles, right? Whenever you have a system of particles, these particles undergo interaction, right? And this interaction give rise to 2 things. One, configuration, and second, there is forces, right? Configuration is characterized by your potential energy. So such a configuration where particles seems to be not interacting with each other, I can consider that configuration, I can assign that configuration as 0 potential energy, a configuration having 0 potential energy. So what can be the configuration of the Sun plus 9 planets for which the particles are not interacting on themselves? See, for Sun and 9 planets, the interaction has got inverse variation with the distance. They are interacting via a gravitational force which has got an inverse variation with the distance. So obviously, if they are going farther from each other, the interaction will fall. The force between them will fall. The interaction will turn weaker. So a configuration where all these 10 particles are at infinite distance from each other can be assumed to be a configuration for which we can assign 0 potential energy. Once you find out a configuration for which the potential energy is 0, you can easily define potential energy for the existing configuration. Then you can find the potential energy that will be equal to the work done in bringing all these particles from a configuration of 0 potential energy to existing configuration. Work done in doing that will be the electrostatic potential, will be the potential energy. I'll come to electrostatic. So for finding potential energy for a given configuration, we first assume what will be the configuration for which I can assign 0 potential energy. That can be a configuration where the particles are not interacting at all. For Sun, for a solar system, the configuration will be when Sun and 9 planets all are at infinite distance. In that case, these particles won't be interacting, and that configuration can be a configuration where we can assign 0 potential energy, right? Then work done in bringing all those particles from configuration of 0 potential energy to existing configuration will be called potential energy. But then remember one thing, when you are bringing those particles from configuration of 0 potential energy to existing configuration, don't accelerate them, because if you accelerate them, it will be doing work more than the potential energy. Then your work done will be partly converted into potential energy and partly it will appear as kinetic energy. So you have to bring them very slowly, quasi-statically. You don't have to accelerate it. You don't have to accelerate those particles. Work done is equal to potential energy only when your work is used up, only in changing the configuration. Work should not go into kinetic energy. Only then you can define the potential energy as work done. Only then potential energy will be equal to, or work done will be equal to the potential energy. See, you are using the concept of work in defining potential energy. Right? We are saying potential energy is equal to the work done. I write the definition, right? I love all this, I write definition. This is how I can write a definition. P for a system of particles is equal to the work done in transforming a system from configuration of zero potential energy to existing configuration such that none of the particle is ever accelerated, or they always remain in the state of quasi-static equilibrium. Not configuration, it's quasi-static equilibrium. See, I discussed with you what is meant by quasi-static equilibrium when I was discussing electric potential. You can just revise those videos, right? The lectures of electric potential. I defined what is quasi-static equilibrium, right? So, or if we assume that interaction has inverse variation with the distance, if I assume that interaction among particles, which usually is the case, every real forces interaction, if suppose interaction has inverse variation with the distance, it can be distance square also, like electrostatic force it is distance square, in even gravitational force is distance square, but then again I'll call it inversely proportional to distance, whether it is distance or distance square, that will call interaction vary inversely with the distance. In that case, the configuration of zero potential energy is the configuration where the particles are not interacting. So when the particles are not interacting, when they are at infinite distance, only the interaction will be zero. So I can say for most of the forces where I can say interaction has inverse variation to distance, the configuration of 0p will involve the particle lying at infinity from each other, particle lying at infinite distance from each other. Then for those particles I can always define potential energy for is equal to the work done bringing all the particle from infinity to the existing position such that none of the particles is ever accelerated, or they always remain in the state of quasi-static equilibrium. Is it not? See, if interaction is inverse variation with the distance, then configuration for which I will assign zero potential energy will be the configuration for which the particles are all lying at infinity, right? So that can be a configuration where the particles are not interacting, or that can be a configuration for which I can assign zero potential energy. So in nutshell, the definition will be the potential energy for a system of particles is equal to work done in bringing the particles from infinity to the existing position such that none of the particles is ever accelerated, or they always remain in the state of quasi-static equilibrium. That is called potential energy, right? That's called potential energy. Then I hope you understand, right? So I'll come to now, I define potential energy for any system of particles. Now let me come to electrostatic system. For electrostatic system, I define the potential energy as potential energy for electrostatic system is called electrostatic potential energy, or simply electrostatic energy. So I can define electrostatic energy as, so I'll say electrostatic energy for a system of static charges, that is electrostatic system, is equal to work done in bringing the charges from infinity to their existing position such that none of the charges is accelerated, or they always remain in the state of quasi-static equilibrium, is called electrostatic energy, or is called electrostatic energy. Electrostatic energy is basically potential energy for electrostatic system. So instead of saying electrostatic potential energy, we just say electrostatic energy. Now electrostatic system can be of two types. One is system of continuous charges, another is system of discrete charges. I'll try to find electrostatic energy for both the system. First I'll try to find electrostatic energy for the system of discrete charges, then I'll move to find electrostatic energy for continuous distribution of charges. Alright.